Hello there, and today we'll be looking at the second experiment topic, which deals about melting point. So melting point is one of the common experiments which was repetitively used uh, in many chemistry laboratories, and it is used because melting point is one of the physical features of a solid sample, and it can also be used to determine purity as well as to predict an unknown sample, for the fact that each of solid samples have their individual melting points. So what's melting point exactly? So in a basic way, melting point is simply the temperature at which a solid compound converts to liquid. And in a science terms, you can define that uh, melting point is the temperature at which a solid and liquid phase coexist in equilibrium. What it means by that, I may further explain it in the second slide. So melting point is the temperature at which solid and liquid have the same vapor pressure. In other words, a solid converts to liquid at 1 atmospheric pressure, uh, uh, which is what we are calling same vapor pressure. So vapor pressure is exerted by any substance, in our case a liquid and a solid, and we call it melting point whenever this liquid and solid have same vapor pressure. So a solid, to talk about melting point, our sample for sure will be a solid, and when you apply a temperature to a solid, the intermolecular attractive forces tend to loosen and tend to be disturbed until each of the molecule of solid randomly moves, and the overall system becomes more disordered. So we said that melting point is a point. Actually, we do not have a single point, and why is that? Again, I may further explain it in the next slides, but uh, in this point, and for instance, if you look at the different states of water, water is ice before 0 degrees Celsius, and water is uh, after 0 degrees Celsius, and water is water after 0 degrees Celsius. So you can see water melts down to an ice, which means the water liquid becomes a water solid in 0 degrees Celsius. By the same token, a water ice will become a water liquid at 0 degrees Celsius, which we call it a melting point, and the first one, the former one, a a freezing point. So it turns out that melting point and freezing point of water are the same. They're just 0 degrees Celsius. That's why in the first slide we said it's a temperature at which solid and liquid of that substance coexist in equilibrium. Going on, so melting point of a pure sample is always higher and very narrow in range. Normally, melting point of any pure substance have between a range that differs in between 1 to 2 degrees Celsius. However, if this pure sample is contaminated, this melting point range will be broadened to 2 to 4, sometimes to 2 to more than 2 degrees Celsius, I would say, because uh, the melting point will be lowered as a result of the impurity, and because depending on the size of the impurity, the range in broadens can go from 2 degrees Celsius to 20 degrees Celsius. So because if you have 99% of something and 1% of something, the 1% is certainly an impurity. However, if we have 50% of compound A and 50% of compound B, we don't say one or the other is an impurity. It's just a mixture of these two. And generally, there is if there is 1% impurity in a given mixture of substances, it turns out that there is about 0.5 degrees Celsius depression from the actual melting point of the pure compound. So let's take two samples A and B with unknown melting point. So the general idea is pure A have a melting point at this point leveled by A, the lowercase a in parentheses, whereas pure B will have a melting point leveled by B in lowercase in parentheses. So when you have 8% of A and 20% of B, which means B is the impurity now, then they will have the C, lowercase c in parentheses, as a melting point, which you can clearly see from the graph that this lowercase c is lower than A. That shows us a depression. So melting point of pure A is greater than melting point of 8% A plus 20% of B. However, if you keep adding more of B, you reach a point where there is no more decrement, right? And that is called eutectic mixture. And the point and the temperature reading at this eutectic mixture is called eutectic point, which is the lowest temperature for a mixture of two substances. And of course, this eutectic mixture is the temperature or eutectic mixture is different for different compounds. For instance, if we take the salt ice, the eutectic point is minus 21 degrees Celsius, but it may not be the same for some other mixture of substances. And this eutectic point for this ice salt is also whenever there is 77% of ice and 20% or 23% of salt. But if you see the case of A and B, you can notice that 60% of A and 40% of B gives out the eutectic point. So in this experiment, we will be experimenting with benzoic acid and 2-naphthol, which you'll take pure benzoic acid and pure 2-naphthol, and then you can take 10% of 2-naphthol and 90% of benzoic acid, and 1:1 ratio or 50% of benzoic acid and 2-naphthol, and then 90% of 2-naphthol and 10% of benzoic acid. So during preparation of these samples, it all starts from making the instruments ready. The only instruments maybe we need for this experiment is a capillary tube and the digital melting point apparatus. So our sample holder for this melting point experiment is a capillary. In fact, we have two kinds of capillary. The one capillary with two of its sides open, which is commonly used in chromatography for spotting samples, whereas this one side open, one side closed capillary is used for melting point. It's called melting point capillary tube. When we have the samples we must have the samples in fine powder. That's because if our powder is coarse, it means that there will for sure be air package in between the samples, which lead to uneven heating of the sample, which ends up to have a wrong reading for the actual melting point of the sample. So in this case, not only if you use a coarse powder over a fine powder, if you also do not pack your samples very perfectly, you may have also uneven spread of the samples, which you will end up in having wrong reading in the apparatus. So it's just you can tap the open mouth of the capillary tube against the samples, and you'll have some powders in the mouth of the capillary tube, and you can then flip it and tap it against the flat table or against any flat support. However, during the repetitive tapping, you may break the capillary tube. So what we were doing back in school was preferably you can find a long stem funnel, and you can put the funnel with the big mouse facing the table, and you can then let go this capillary tube with the narrow mouth of the funnel, and you can do that repetitively, and you will have the sample packed packed perfectly in the capillary tube. If you do not have a long stemmed funnel, you can use any narrow glass tubing. You can if you have small measuring cylinder or any narrow and long glass tubing, that also works perfectly for packing the powder in the capillary. Again, how amount should the sample be in the capillary tube? So if you have too small sample, the problem is you may not see the sample while you are measuring the you may not clearly see the sample while you're measuring the melting point in the apparatus, and you can have also a problem of a problem of overheating. Like if it is very small sample, it might not stand to wait the range. It may melt out even before it reaches the range, because it will get the heat uh, entirely, and it will end up melting. So the recommended amount of sample that should be in the capillary tip is from 0.5 to 2 is, I think, good, to 2. In case of centimeter, yeah, what you should be careful is that if you have too many samples in the capillary tube, the sample will encounter uneven heating, because what happens is the bottom tip of the capillary tube will heat first, and if the sample is packed too much, then it will take time and more temperature to heat all the sample all the way up to the top of the sample, which will give you wide range. Even if your sample is pure, because you have used a lot of the sample, you may end up having wide range temperature. So uh, it's good to use a sample amount within the recommended range. So in the actual experiment, we'll be using a digital melting point apparatus, and while using this, the sample in a capillary tube will be placed in the port available for the capillary, and you can adjust the temperature at 1 degree Celsius per minute through the entire experiment. But if you do not have that much time, or if you lack the patience, you can adjust the temperature to about 5 degrees Celsius per minute for up to 80 degrees Celsius, and then you can stop. You can readjust it later on for 1 degree Celsius per minute once it reaches the 80 degrees Celsius, because both 2-naphthol and benzoic acid have melting point greater than 120 degrees Celsius. So if you can run the temperature increasing by about 5 degrees Celsius per minute up to 80 degrees Celsius, will not have such an effect. So what happens is, when you measure the melting point, you have to record the melting point in ranges. So the time to record the first range is when you see the sample get shrinked or diminished, or for that matter, in some cases you may see also the sample getting wet, or you can say it's a drop. Maybe some part of the sample will become like a 1 drop of a sample, or a 1 drop of a liquid, and then that's a time where you should record the melting point, the initial melting point. Whereas the final melting point should be recorded when the entire powder becomes a liquid, right? Nowadays, all labs have this modern melting point apparatus, but because this melting point experiment has been done since so long, it's not also that necessary to use the or it's not also such crucial to use the digital melting point apparatus. You can also do it in a test tube tied to inside a beaker. So the operation is very simple. You need to tie the capillary tube against the thermometer and dip it in a paraffin oil, because paraffin oil has a boiling point more than some of the solids, and it can use as a media to heat up the solid sample under study for melting point. We do have also another technique of doing the melting point experiment with the Tiley tube, and the operation is similar. The way you tie the capillary tube with the thermometer and everything is almost similar, but this using Tiley tube is more safe and more efficient than using just a test tube, because even if you see the heat source, the Bunsen burner is placed in the arm of the Tiley tube, which means there is no direct heating of there's no direct heat going on into the sample, which will give us preliminary results, which will also deform the sample before the actual temperature has reached. So again, we use oil because oil has greater melting point, boiling point than some of the solids, and yeah, the remaining operation is similar to the one we use using a test tube. And so once you conduct the experiment, your next task will be to put down the data, and the data can be recorded in with respect to each sample, and obviously you will have you can just take the melting point of the pure samples directly because they are known, but because you'll be measuring them, you can also put your reading directly into the table. So you'll be finding when you draw a graph from your results, you will look such a kind of graph, which the above line is for the melting point of all the pure samples, where the red point is a melting point for the mixture of sample, for the sample with impurities. That's why we say melting point of pure sample is always greater than melting point of a contaminated sample. And the lowest temperature you'll get from the below line is the ejective point, where it is the lowest point created from the mixture of these two substances, from the 2-naphtol and the benzoic acid. And to the safety matters with respect to this experiment. So in this experiment, we'll be using benzoic acid and 2-naphtol, and which of course if we have leftovers of benzoic acid or 2-naphtol, or the papers we use to measure this will be waste products, okay, and they should be kept under different waste containers. Again, the capillary tips are not going to be used again, they are disposable, and they should be kept in a container leveled with glass, broken glass waste container. And also it's also an experimental task to remember, which is a critical task also, to remember to turn off and return the apparatus back into its respective shelves. So that's all regarding this today's experiment. And again, if you have any comments, any questions regarding the experiment, I will look to see it on the comments on the YouTube. And thank you very much for your time.